Ask questions, and I'm not going to be embarrassed if I say things that are so simple that all of you already know it. Okay, so you always learn something, I believe. Okay, so here's my little take on why this is an important, has always been an important problem, and right in the middle of quantum mechanics. A couple of years after the very first paper on quantum mechanics was the Pauli exclusion principle and Fermi statistics. Pauli visited Fermi in Italy at New Year's on those dates, and these ideas were emerging. Thomas Fermi approximation. Dirac made the first density functional. It was a Thomas Fermi approximation for kinetic energy and the exchange energy for electron gas. So density functional. And already in 1928, basically the equations were there. So here's my title. I wonder if you can guess where that gets to. So already the Bloch theorem was in 1928, which was of course known before, and other people had done it before. Bloch did it very nicely. Wilson apparently was the one that sort of put it together and made it clear that now we had a theory for understanding why some things were insulators, why some things were metals, based on the independent electron picture. And that led to the understanding of semiconductors. And look at some of the names of people that worked in that period. Wigner and Seitz did the first quantitative calculations for material like sodium. Slater's augmented plane wave method was already proposed in 1937, and he did calculations of bands of early 30s. Shockley at the same time student of Slater, did calculations on sodium chloride. Bardeen was a student of Wigner, is the one that pointed out the Hartree-Fock disaster in metals. And you might notice that two of the three inventors of the transistor were students that did their calculations, did their PhDs on electronic structure calculations. So you have a challenge. But, and then of course there were the methods invented, and essentially every method that we use today was invented in the 30s, almost. So Slater's augmented plane wave, Herring did the orthogonalized plane wave toward the end of the 30s. The first calculations that were used this method for the bands of semiconductors, so that was in the 50s. Hellman and Fermi already had the pseudopotential idea. The method that was used is very close to the ideas that have finally developed into norm-conserving pseudopotentials. In fact, Fermi wrote two papers, one on scattering of neutrons from nuclei and another on scattering of low-energy electrons from atoms, and he had the same figure in the two papers. That was basically the pseudopotential. The KKR and methods came a little later, and then there was a development in the 70s that really made a difference for the APW methods and the new method, the LMTO, Anderson in the 1975. Okay, of course, many-body interactions were just known at that time, and it was, people worked on independent electron approximations, but they knew it was an approximation. So already in 29 was a calculation of hydrogen 2, essentially numerically accurate by Hilarius. Then it was the 50s that we really had the advances in many-body theory, these famous people that we know that's developed the methods. And Monte Carlo started in the 60s, and basically at this kind of time period it was a free electron gas that one could work on. So here I want to do it a little bit more concentrated on just one panel, But the major point is that there really was a turning point in the 1964-65. It's when it started the ways that you could actually make quantitative calculations. So, same year, Bill McMillan did quantum Monte Carlo calculations on Bose systems, and density functional theory was invented by Hohenberg, Cohn, and Sham, and Hadine's GW approximation for excitations. And if you notice, those are the three methods that are most used today. In the 70s, then the computation really came in to make these methods really feasible. And then Carr-Parrinello made this enormous difference in the 80s, and the QMC and then the quantitative GW really moved on. And so now we're at the stage of, I would say, in particular, combining density functional, maybe density functional ideas, maybe density functional quantitative numbers, and the many-body methods to make more computational, not just more accurate, more complete information on systems. And of course, I love the things like polarization and dynamical mean field theory that we'd like to mention at the end. Okay, and notice, and I'll try to do this all along, that I will say many-body in quotes, because DFT is already a many-body theory. It's just you're able to do something with independent particle methods. So this is just a slide I have available, just to get this point that I like, is that you want one method that deals with a whole bunch of systems. I'm not trying to make the computer just push a button and you get an answer, but we'd like to be able to see how well basic approximations apply to a whole range of things. So now I want to get to the point that probably most of you know very well, but maybe not exactly the way I look at it. So emphasizing over and over that it's a theory of the many-body system, and there's this famous Hohenberg-Cohn theorem that says you can get anything, but there was a Cohn and Sham that really made the step that was important, and that was that you could get some properties of a many-body system and not other properties, and if you set that as your goal, then you could cast the theory in a different way. I think that's something for us to remember for other problems as well. And I would say that the great thing about density functional theory that was made possible by this step was to allow you to come up with approximations that turned out to be very good, and but that was the sense in which it's really, really useful. Okay, so now you probably don't have questions right at this moment, but get ready and please have them soon. So we want to say that this is the big problem we want to work on is interacting electrons. There's a nuclei, and they interact with the nuclei. Then there's nuclear terms that we'll just say that's off to the side, but we add them later. And there's the kinetic energy of the nuclei, and that's what we're going to omit at this time. You can put it back in then in perturbation theory. Okay, but that'll be the assumption from essentially in this work and essentially all the work. And so we'll view the problem as electrons, that's in this square box, with an external potential. So again, this is the total energy of this interacting many-body system, and it's a kinetic energy of the interacting system, the interaction, the expectation values of the interaction operators, and the special thing that's used in density functional theory is that the electrons couple to the rest of the world only through a potential and its density. And of course, the minimum energy is the minimum energy by the quantum mechanical expressions. So we have these terms, and sorry, I've already said these words, but so the nuclei and everything else is meant to be external to the electrons. And so we have this famous problem. I like to say it this way. Schrodinger told us you start with a potential and you get an answer in principle. And Hohenberg-Kohn said that the density also implies the potential. So in principle, all properties are determined by the density because the density determines the potential. And I just want to get this point of what a functional is, that the functional, and try to use that consistently. The word functional means you take an entire function and you map it to a result. Sometimes it's a function, like in some simple cases that we'll do, but in general it's an entire function of space that you need to map to the final result, like the energy. And I think it's really interesting that Mermin extended this to the density at any temperature should be enough to predict the thermodynamic quantities, entropy, anything like that. And in my little announcement, I kind of used this offhand remark that why doesn't anybody do this? And one of the people talking to me says, well, I do it all the time. So there's two definitions around, apparently. One is putting temperature into the Kohn-Sham formalism and then making a functional that involves temperature. Mermin, I use the term, as Mermin, as I think he did, was that it's one of these in principle exact things. And you might ask me a little later, why is that harder to do than the ground state? Or you think about it, rather. Maybe you'll answer it. Okay, then everybody knows that Hohenberg-Kohn theorem didn't get you anywhere. It didn't give you any hint of what to do. But the Levy-Leib functional really tells you what it is. It's do a two-step process. Minimize the energy as a function of the many-body wave function at fixed density, and then minimize then that's a functional of the density, and then minimize the energy as a functional of the density. So that really tells you what it is. Set at a particular density, and you find the best configuration of the interacting electrons. And then that is it gives you the density functional. And as a mathematical point, this a functional needs to be defined in some space around the minimum, because it's a functional and you minimize it. And this tells you what the space is. If you go away from the ground state density, then it's set at a different density, and then the many-body wave function is different. That gives you the lowest energy many-body wave function is different at that density. So this tells you really what it is. Okay. Now I'd like to ask you, why is a density functional good? Is it better to think about the hard part of the problem? The fact that it's interacting electrons that have to obey the exclusion principle as a function of the density or the potential? I'm going to take that back because I meant to have the second line not appear on the screen. So is it better to think about something about this hard part of the problem in terms of the density or the potential? One goes, one determines the other. Think about it in two ways. Think about just a homogeneous electron gas, or think about a charge varying like an atom or a solid. Which makes more sense?
This.
Okay, why? good. Somebody said something. Well, you know, physical reason for why the density would be good. I bet you know it. That's one case for sure. The electron gas really gives you a hint, since the potential is just a constant and is irrelevant. But density functional theory was around before Hohenberg-Kohn. It was using classical liquids. And if you think about it, suppose you take a big chunk of liquid and say you put pressure on it. Pressure is the external variable, like potential is, and density is the internal variable. And if you're down here inside this piece of material, I think one atom cares about the neighboring atoms, and it could care less about the pressure, except that you have to have the corresponding pressure down inside. But it really cares only about for the hard part of the problem. The correlation between atoms is correlation between neighboring atoms. And then that depends on how far apart the atoms are. And so density really makes sense. So basically we would say it just really makes sense to consider the density as the quantity to which you'd start making approximations. And the same idea that I will claim for the electron system. I drew something here that's like a hydrogen atom. Well, not quite. By something that has a maximum. And if it's one electron, then I think, or two, then it's pretty, you know, it's pretty similar ideas. But if you have hundreds and thousands of electrons, and this is describing a large distribution, then it's clear the density is a good idea. And then we find that it's a good idea in ordinary atoms as well. Okay, so the auxiliary system then is what really made this useful. And so now I'm sure you know this, but be thinking and ask, you know, make comments, please. So we start with the non-interacting electrons that are Kohn-Sham ions, and we use the idea that if you require that the density of this non-interacting system, I'm using the same label for the two sides because they're supposed to be identical. So this is the non-interacting problem with the Kohn-Sham potential that goes through to find the density. And the Hohenberg-Kohn theorem applied to this non-interacting problem says that the density implies the potential. And over here it's the interacting problem. And through the Kohn-Sham connection, you can go from any point to any point. So the idea would be, if you had the exact formulation, the Kohn-Sham potential determines the many-body wave function. Okay, pretty idea. But the only thing that was required to be the same with the, sorry, my pointers seeming to run out. It's not that important. The only thing that's really required to be the same is the density, and then the energy for very good reasons. The good reason is that you want a functional that you can minimize to find the correct energy. Excuse me, find the correct energy and density. So you should get both of those out of the calculation. So here's their expression for the energy. Everything that's easy is in these terms, and then everything hard is buried in one term. So we'll consider that the independent electron particle is soluble. Okay? And we'll consider that the exchange correlation function is there, even though we don't know it. And this is, I just want to emphasize it over and over, this is what was really good about the approach, was that you now can start making approximations. And the Kohn-Sham equations then are just the variational equations. So we now vary the Kohn-Sham energy with respect to the orbitals, and the orbitals determine the density. So it's a chain rule kind of argument. And so finally you get this equation, that's the Kohn-Sham equations that you need to solve to get the minimum energy here. You know that there's other ways to do that, right? You don't have to go through that equation. What's another way? What was that?
Variational principle.
Use variational principles in different ways. Like how else can you get to the minimum of a function? You don't have to diagonalize the matrices always. How do you get to the minimum of some complex function? What are some mathematical ways? You know. I think I heard. Steepest descent. You know, just any kind of method that'll get you to the bottom of that energy, it will get you there. And of course, that's what's used so much nowadays, because it's efficient. Okay, so here's the picture. I'm sure you, well, I keep saying I'm sure. I know most people in this room use this, except maybe in a more efficient way. That you start with a density, you get a potential, or you start with a potential, solve the equations, construct a new density, and go around the circle. And then you get this Kohn-Sham, this energy, as a functional of what? I'll get to this in a little while. Because I want to. What if I use a functional?
Richard used the spin index in there on the density, which I'm not sure Kohn-Sham used, yeah.
Oh, maybe I did something. Just put in what? Sorry?
You slipped in the spin index, the up and down arrows.
Oh, so I slipped that in, okay? I even forgot it was on this slide. So I suspect Kohn-Sham knew that, but you're right, it's a generalization, and we'd like to keep that in mind. That's a kind of generalization of the original theory, and let's see now, that's an important generalization, isn't it? Because like Hohenberg-Kohn said, if you know the density, you'll get everything. Is it different in Kohn-Sham? Think about that. Okay, think about it. So what I wanted to do was right on the board was to be clear, there are more than one functional that people talk about. And just to want to be really clear on it. You know, the deep functional is the exchange correlation functional, the density. And then that's used of local density approximations, the gradient approximations, etc. And so that's, of course, the basis of the theory. There's other functionals that get to the total energy. And it's worth mentioning that to keep it straight. So in principle, it's a function of the density, right? Now that was the whole theory. But in practice, what's it a function of? Since this is equal to the kinetic energy plus the potential energy plus, well, that's the potential energy plus E, and then this would be integral of B Kohn-Sham, or N of R. Have I missed anything? Yeah, I did. Because you have to subtract the double counting terms. And you correct me if I make a mistake here. It's wrong one more time. Minus the exceed. Plus now that I get it right, so that's sum of eigenvalues basically, and this is the corrections. And these are simply function. That's easy. This is the Coulomb energy is just a function of density in an easy way. How about the kinetic energy? It really is. I mean, in practice, then in principle, it's a function of the density, right? Okay, so is there something simpler than the orbitals? What determines the orbitals? Potential. So look where we've gotten. So in practice, what we have is a function of the potential and the external potential, because the external potential determines the density finally, and the density is buried in the exchange correlation function. So in practice, it's a function of the potential. But down at the most important still, we still basically have this exchange correlation as a function of the density. And now some changes beyond Cone-Sham will go somewhat beyond that, but that's what it is in Cone-Sham. Okay, so it's useful to keep these in mind, even though when you finally get to the energy, it's it should be the same when you get to the lowest energy. Okay. So I want to give you an example. It has to do with density. Key thing about the exchange correlation is it's the interaction of an electron with the other electrons, and only the exchange correlation part. So we'll assume that all the electrons are smeared out and we get this Coulomb potential, called the Hartree potential. And then everything is different from that is the fact that if one electron's at one place, then the other electrons are pushed away. And it's the interaction, Coulomb interaction of that electron at the center with this lack of electrons around, which forms a whole charge density. And that's spherically symmetric because the Coulomb interaction is spherically symmetric. It doesn't care which direction. So let's look at I've forgotten what the question's going to be. It's probably going to be, is the density better? Right, that was the question. So, which is it? I think you already knew the point. But so this should apply to quantum systems as well. Right, let's go ahead. So now let's look at the approximate functionals, and then I want to get to the examples in just a minute. So we know what the local density approximation is. It's saying that at every point in space, it's the electron acts like it's in a homogeneous gas of that density. And so it's local. So finally, it's written in terms of a function, just a value at a point in terms of the values of the density at that point. And of course, this makes the point that in order to get it, you've got to do a many-body calculation. So you have to do a many-body calculation and then have the approximation of how to use it in the Cone-Sham formulas. And these various gradient approximations then go beyond. So here's an example. This is the neon atom. And this strictly is only the exchange part, because that's something you can calculate exactly, and it was done before, but the correlation is similar. So here's what happens in a neon atom. The nucleus is at the position of the blue line, and it's centered on the on an electron. You say, if the electron is at this point, where is the missing electrons in this Hartree-Fock calculation? So that's straight in a Hartree-Fock calculation, and in fact, the missing electrons are over near the nucleus. So you say, if one electron is here, where are the other n-1 electrons? Actually, I should say that differently. If you know the total density for n electrons, and if you put one of them here, then there must be one missing in the rest of the atom. And that missing one is mainly missing over near the nuclei. Now, would you consider this a good approximation? This is a local density approximation, which has to be symmetric around that point. And that's the real thing. Doesn't look like a very good approximation, does it? But remember, it's only a spherical average. Let's do a spherical average around 0, around that point, and look what the difference. Now 0 is here, and this is the radial density distribution, and that's the exact, and that's the local density approximation. So you immediately get a sense of why this could be a good approximation for the ground state energy, because that was what was involved in that spherical integral, even though it makes a terrible approximation for what's actually going on. But that's what was the idea. You're supposed to get the density and the energy, and nothing else. So it just doesn't give any picture whatsoever of actual correlation, and when you start looking at things you can look at, like the exchange, it's just terrible. Even though the energy is very good. So another thing that's true is that the energies for individual states, like to remove an electron or to add an electron, are pretty far off, even though if the ground state energy might be very good. Here's a couple of figures. This is for beryllium, anyways, for 2 electron atoms or ions. And the dotted line is the density functional potential, the Kohn-Sham potential, and the solid line is the actual potential that this electron would feel. And you can see what's happening. An electron outside this ion is feeling a Coulomb potential that goes on out this 1/4 distance, and the density functional, however, depends only on the density, and it goes to 0 much more rapidly, like exponentially. I have to admit I'm a little confused. For an ion, it shouldn't do that, but at any rate, whatever it is, if you have a neutral atom, the density potential goes to 0 as the density goes to 0. And that's not true in reality. If you pull an electron off, you leave a charged system. Okay? So that will be much more important in these excitation energies than in the total energy. And yes, please.
Sorry, what's the curve at the bottom? That on the curve.
Oh, well, I pull this out and try to remember. Oh, that must be the density, right? This would be a radial density, and I'm not sure if they. Well, I have to admit, I forgot to check this carefully when I was actually doing it. But the idea would be that even though if you got the density right, you wouldn't get this property right. You could get the density or put it another way, I can't remember this actually to work, but you can take an exact density and work backward to what the cone channel potential would be. And then you can look at what the eigenvalues are, and you say that this exact cone channel potential gives you the wrong eigenvalues. I think somebody else. Thank you. So that's one of the nice things is some people talk about exact cone channel, and you can work it out, work backwards from some exact calculation you can do on small systems. And I actually had the number somewhere for neon to that was supposed to be for neon, and then I couldn't find it when I was making this slide. But it's really true. To pull an electron off of neon, it's a factor of 2 from the correct answer. On the other hand, we have this beautiful result that happens for the total energy of hydrogen. And here's a figure. This is the exact calculation, and that's the local density approximating. So for the energy and the distance, it's just exceedingly good. And the curve that you may not be able to see is, I think this is Hartree-Fock. And this is where it just goes terribly wrong at large separation, but then you can get an unrestricted Hartree-Fock that goes back to the exact answer for two separated hydrogen atoms. So anyway, to me, this is the answer for why we think density functional theory has any hope of being good. You know it's exact for the free electron gas, and you know it's almost perfect for a bond, and so it has a good chance of being reasonably in between. So I didn't say it completely right. What is there something in common between the neon atom and the hydrogen molecule?
Closed shell, I suppose.
A closed shell, right. So it was easy to do some calculations, and that you should at least start worrying. Now, did we choose examples where it works? And that's clearly the case, but we don't quite know the reasons. Like if you take some famous transition metal molecules that have open shells, then it doesn't work so well. So there's a case, particularly open shell systems that are highly compact is exactly the place where it doesn't work as well. And similarly, one of the famous problems is, I think I've talked to people about this, is that if you have a material like zinc oxide that has the zinc P states and D states are just a little way down, and they're given pretty badly in terms of their positions, their eigenvalues, how much energy it takes to pull an electron out. And that's exactly the same problem as in neon. That you pull them out, it costs too little energy to pull an electron out. So you make it so in those open shell systems you can get the ground state energy pretty wrong, and in these closed shell systems you may get the density right and some total energies very well, but the energy to remove an electron can still be very bad. That was this point that if you don't have large gaps to excitations, then you can kind of see why the density functional might be giving trouble. Oh, I forgot that line was there. I should have put it up just a moment ago. Open shell systems are more correlated for very good reasons. Because of very low energy to move electrons from one state to another. Okay, for how well a generalized gradient approximation works, this will show you why, quantitatively, and this shows you, at least in my estimation, several things about it. If you define a gradient, this is supposed to be a normalized gradient it's dimensionless. It's a gradient of the density divided by something that has the units of gradient of density. And the calculations are done literally for a homogeneous gas in which you've imposed a sine wave, so that there is a gradient of the density. And the calculations have been done by Monte Carlo, but here I'm just showing this is what the functionals do that have tried to reproduce these many-body calculations. So if you, and what's plotted on the vertical axis is the ratio, the enhancement, and x is the, I hope I'm going to say this right, it's the ratio to what it would be for the LDA. It's a function of x divided by the at zero gradient, and the correlation is the same thing, except it's divided by the exchange number, which is just a scale factor, but this helps you understand in a few places what's going on. So horizontal would be just the local density approximation and independent of the gradient. Here are the forms that are some of the favorite ones that people use, and at small gradients, and typically 3 or 3 up to 5 is the place where you find gradients and materials, that all these functionals are about the same, and they increase the exchange, increase the magnitude, it's a negative number, by a factor of about a third or around that amount in this range. A huge change. Huh? Look at the correlation. Look what happens to it. It almost dies by that point. That make sense to you? You confine the electrons by a potential. They get more dense in the one region and less dense in another region. And the correlation energy goes down. That make sense? It goes down relative to the exchange. And if you think about it, that's actually what happens. If you go, like in an atom in a core, the correlation energy definitely gets bigger in the 1s electrons of uranium than in the 1s electrons of helium. But the other energies are getting much bigger. Like the kinetic energy is going like the 1 over the square of the distance, whereas the potential energy is going like 1 over the difference, 1 over the distance, and so relatively speaking, correlation becomes less important. And it's almost true that the correlation is not that important a factor. The exchange has gotten to be the big number and real problems. Isn't that amazing? Amazed me. You come from a condensed matter background and you think, oh, exchange is easy and correlation is hard. And suddenly you find that exchange is big and correlation is small. And there is where all the approximations come in, trying to approximate that big exchange number. I mean, that really is the difference in a lot of the approximations. I mean, the consequence of what those approximations are doing. Okay? So here's some numbers for a whole bunch of functionals. PBE is my favorite, and everybody's favorite almost, and because you can understand it. There's an actual few-line derivation of what it is, and whereas the others are really hard to figure out just what they were, what they are, and how they were derived. But here's the some of these atoms that tend to be closed shell, you might have noticed, and the first one is hydrogen, which you can see how bad you do. So anyway, if you look at the local density column, and then you look at all the gradients, you see that the local density is pretty bad for the exchange and the correlation, and every other one gets a much, much better. And what happens is that the, let's see if I can see this right. Oh yes, this would be the point. That the exchange increases starting from the local density approximation to all the better ones, and the correlation decreases when you start with local density and you go to all the improved functionals. Maybe that's not. Yeah, that's true, I think. Every single one. So that's what's going on with those functionals to make them work better. Yes?
Would you actually use for getting the exact numbers?
You're pushing me. I got this table a long time ago, and I think it's from quantum chemistry type code, configuration interaction. Except I think neon wouldn't be quite that accurate. Some of them, no, I'm pretty sure they were not from Monte Carlo, although you could get this with that kind of accuracy. Of course, the top line is just Hartree-Fock, and then this next line is the answer minus Hartree-Fock. And so these are just easy to get, and all of these one would have to get out of a many-body calculator. Sorry, I don't know exactly. Okay, so you see the direction things have gone, and you see that one going up and one going down is something that kind of helps you for accuracy purposes. And it's a famous one. If you try to do the exchange better, remember it's the big number, if you try to do that better, it's really hard not to mess things up. Because there tends to be cancellations going on. Questions? Yes?
So you said correlation goes as like 1 over R, but exchange goes as, is it 1 over R squared?
Yes. No, I probably didn't say that quite clearly enough. So the kinetic energy always goes like 1 over R squared, and both the exchange and correlation should go like 1 over a distance, but in fact the exchange just gets bigger. And you can do those calculations even, like take an infinite two-dimensional system of finite thickness and do the calculations of like a wave function that's just a good old sine wave or cosine in the perpendicular direction, and you can calculate those numbers and for the exchange, and you'll find how it goes. Correlation, of course, that's harder. Okay, I put in way too many slides knowing that is too many, and it's for discussion is to see how far we get. This is my favorite table to emphasize that we've gotten to the place now with different methods, calculational methods. The norm conserving pseudopotentials, PAW, any one we want to talk about later is you should just say well, we can get the answer out, if you do it well. And the answer is very close to experiment. And this is all, I think, with this PVE functional, I think. And when you get to iron, it's not quite as good. And the moment you get the iron moment, actually, rather well, well, I'd say that's very well. But some of the terms are not as good, and like, for example, the bulk modulus of calcium fluoride. And there you're getting more of a difference between this APW method and the pseudopotential, and that's because the core in calcium is not so deep, and the pseudopotential approximation is not so good. So at that level, we're saying we're not quite getting the same things. Okay, let me see what's next. Kind of forgot. So this was upon a Monte Carlo calculation of exchange and correlation holes in silicon. Put an electron at the center of the bond and look at the absence of electrons around it. And the exchange has to integrate to one missing electron. Okay? And it's this big thing. The correlation doesn't. It's just how the other electrons respond, and it can be positive or negative. The exchange is negative definite. It just can't be positive. So that also gives you the reason why this is such a much bigger number than this correlation number for the energy. And it gives you some idea that things are reasonably localized. And this was, note the scale again. This is a much bigger scale than that one. Okay, I'd like to get to functionals of the wave function, but we're about out of time. So let's just get the idea. The cone-sham already is a functional of the wave functions because you didn't know how to do the kinetic energy except with wave functions. And so in a way it's logical to go the next step to make these I should have said EXE functionals of the wave functions. And I've said cone-sham all along, but this, in a way, this is still cone-sham. It's maybe it depends on your definition of what cone-sham means. But here's one. Let's take the exchange to be just what you get in Hartree-Fock, which would just be the integrals of 1 over the Coulomb energy and two densities that's made out of cross products of wave functions. So just Hartree-Fock, but you require that the wave functions in that expression come from just a potential, like in the cone-sham approach. So if you think of cone-sham as everything starting from a potential here, then the wave functions come from the potential, like the kinetic energy, and then this is just something to evaluate. And if you do the non-local exchange, then you get the gaps to be really very good. This was the semiconductors, and that's the local density approximation where germanium is a metal, and this is the, on the line should be the correct, agree with the experiment. And so these are some calculations, just making that change. So the total energies are a little worse, I think. And you can, and it's also added a correlation that's just a function of the density. So it's just a sort of an add-on, which is not so important for this property. But it's improving that exchange is the big item for improving the eigenvalues. And it doesn't, it was already pretty good for the total energy. And so you just wanted that agreement not to be destroyed. And when you get to these cases like open shell systems with transition metals, then this also helps. I mean, things like this help even for the total energy. Now, I think I can essentially stop almost. So this is actually harder than Hartree-Fock, because you have to search for a local potential that will be consistent in the end. And Hartree-Fock, on the other hand, you just take an external potential and you just do the calculation. And so this is what's done in chemistry a tremendous amount, is you mix Hartree-Fock with density functional, and Purdue has this magic formula that you get from theory that it should be a fourth Hartree-Fock and 3/4 density functional. And you might suspect that he had already looked at the fact that if you do that, your band gaps are pretty good. The Hartree-Fock is way too big and density functional is too small. And so this worked out very well, but he had a theoretical reason as you integrate up from non-interacting systems to put in the Coulomb interaction. So really very pretty reasoning. And then that's been fitted in much more carefully by other people, so it's not just this simple formula. And I believe firmly that the reason Cohn got the prize in chemistry was simply that the functional has gotten so accurate that they were really useful in chemistry. Okay, so now we'll get to points that I definitely can stop. Any other questions, or shall we just break?
I mean, density functional theory is not supposed to give you excitation energies, right?
Right, exactly.
So why are you so happy that you've got a better functional, which apparently better, which gives good excitation energies? It might be a worse functional.
Good for you. That's exactly the point, isn't it? So you've decided you're going to ask for something that wasn't in the Cohn-Sham approach, and so that Hartree-Fock plus DFT, that's definitely not Cohn-Sham. So it's going beyond, and so then you can view it that way. You said, now I want to do better, and so there's kind of two ways. It's a real theoretical approach to do better, and it's a empirical or hand-waving approach just to get answers that are better. Yeah, good points.
Okay. There is tea and coffee here, I believe. We've slightly underestimated how many of you there will be here in terms of number of mugs. So if you're a resident in this building, I'll ask you to hold back, because you can probably remit back to your office and get your own appointment if it turns out to be necessary. The other thing is there's hardly any space around this table. So once you've got your tea and coffee, if you can kind of then sort of leave the area as rapidly as possible, that would be very helpful as well. But we'll start again at 5:30.
Okay, great. Thank you.
Until, yeah, this is E. So you're going to obviously, when you do it, you're going to get integral of sigma d e. No, you don't have a half.
That's what I'm saying, yeah. So you're not going to get a lot.
Yeah, no, actually,
I think there is no half, but he
I don't
wrote
think
it
there
right.
is a half there. I think it comes.
It comes after integration.
Hang on a minute, let's have a look. I think it comes. Yeah, I think it's an integration factor actually.
Oh.
Yeah, yeah.
Here. I see a question.
Yes, it's actually on what you said before. You were talking on infinite energy functionals that were widely used for chemical molecules. But I wanted to know why does it work?
Why? What doesn't work?
Why does it work? Why taking infinite functionals work for these kind of molecules? Like what's the physical reason?
Oh, I think the physical reason really is that in small systems, the Hartree-Fock gets you something that's quite important, and it's non-local exchange. The fact that you have a wave function that extends over the entire molecule, and it has this interaction of exchange with other wave functions that extend over the molecule, and this local or gradient approximations just do a poor job of that. And identifying a point in space and trying to approximate what's happening with these wave functions. It's, I may not be able to say it any better than that. And well, there's one more reason that the density functional was badly looked upon in the chemistry world for a long time. It was just considered dirt. And one reason is that you don't even have the right ordering of levels, that you don't have the proper excitations, because you just have this ground state problem, and then when you do, if you had the excitations then are just the independent electron excitations of that one fixed potential. The proper singlet, triplet, all the things that are just come directly out of the Hartree-Fock, even if the values may be wrong, but at least in principle you have all the states that you just don't have in density functional. Now that people are doing very big molecules and more accurate functionals, then it becomes very useful in chemistry. I'm going to turn to the next talk, but this was the last slide of the previous one. I just skipped over a bunch of this application kind of stuff that was just thrown in. You can do a better job than I can at that. And I've used a word that I hate to use, failures. And if I was more careful, I forgot, I would have put quotation marks, because the failures are where it's not supposed to work. But this is what people call failures. The excitations, the strongly interacting systems, now that's maybe really is a failure with ground state. And the van der Waals is something to emphasize that you can't get it out of a local approximation, but in principle it's in the functional, and in practice very good functionals have come around just recently. So I say solved, I also should put that in quotes, because of course it's not solved perfectly, but the principles are there and very apparent, and pretty good results.
How about the image problem in surfaces? Is that solved, or would you say it's solved?
Well, the van der Waals forces near a surface actually come out, that's part of the theory. And the image problem, think about that. Is that just part of the Coulomb problem? No. I think it is, right. So that's solved.
You've left a hole behind.
Yes, right. But really what happens is you have charge on the surface that mimics a hole behind, right? So I think that's solved in the basic sense. But I may be wrong in my thinking there. Okay. What I need to do is get one of these other things here. Sorry, I just can't see. So this was supposed to be about methods. And my purpose in talking about this is that if there's a great danger to let plane waves, or in this institution, grids and clever things to do with grids and order in to sort of be everything. And I'm not criticizing anybody, just that's my take on things, to see what other methods can give that are really useful, and similarities in fact. And I discovered one in talking to people today that I didn't know about. Oops, wrong there. So I would say that every method is designed to deal with the core problem. Now that doesn't mean exactly core, but it just means that things are strongly varying near the nucleus. And in some cases it's actually dealing with the core. In other cases it's dealing with the effects of the core. But every method is trying to deal with that. So there's 3 ideas, 3 methods, and I've done this before with classes where I literally refer to these chapters in my book. But the linear combination of atomic orbitals, which just makes total sense in a lot of cases, like the core states, they're just there. And the valence states are pretty atomic-like in many cases. And you get a good feeling for things with these functions. The plane waves are just very, very general, and they can be applied to so many things. Very simple, but one of the things I would say is that it's really hard to get physical insight from looking at a lot of plane waves. That's my limitation, and you really need to use pseudopotentials. And I think that's true for grid methods and a lot of methods. And the augmented methods are ways to get the core into the problem while using plane wave-like advantages in some other parts of the problem. So everything is trying to deal with that, I would say, all methods. So the good thing about linear combinations of atomic orbitals is that they're atomic-like, and the bad thing is they're atomic-like. And I would say there's one way to see this that will couple to something else later. And I learned today that it couples to some things that people do here. Oops, well, that's all right. I don't have to pull that down. Suppose you have an atom and you have a wave function, let's see, potential, a wave function that somehow does wiggles near the nucleus. And we'll make that extend a little further. Same thing on this side. So we have a wave function around an atom, and this part in the center is really atomic-like. And the tail in an atom is rather different from what happens in a solid. So you've got to fix this in the solid. And here's one of the worst problems, in my opinion. Here's the next atom, and you know that the wave function over here looked just like that one. Is already very good. You know that that's just about the right wave function, and yet you stuck on top of it something that's wrong. I mean, the tail of that function just should not stick into that atom. And so you start building up having to use clever atomic wave functions and further and higher numbers of functions than you need, just to get rid of a problem that you just knew was there from the beginning. So if you can have a function that goes over to the next atom and then looks like the proper function, you can do a lot better. Okay, so to me, that was like the biggest problem for quantitative things. And they're just great. A small basis set is sufficient for semi-quantitative kind of work. And larger ones, you can really do a good job. And Gaussians are just wonderful. They're not atomic-like, but all the intervals can be done analytically. And of course, they're nice for localized systems. And I'd like to comment on this relation to other methods. This aspect relates to these for LMTO, linear combination of Lafayette orbitals, that's done later. And it either is already in the one-step ideas or it could be. I don't quite understand. So I'd like to go through this quickly. Like I said, I made extra slides so I got too many. But it's just to set up things, and I'd love for somebody to ask questions, please. Because there's a number of things that we just don't have to do. Okay, so the basic thing of these localized bases is you choose them in advance, and you calculate matrix elements. So the entire problem is cast in terms of, anyway, wherever it is, there's the equation. So it's the generalized eigenvalue equation with Hamiltonian matrix elements, overlap matrix elements, and so this is the linear equation you've got to solve. And you get these from matrix elements of the Hamiltonian. We're going to divide it in two parts. Calculate the matrix elements and use them. And using them, then you have a lot that you can do. If you calculate S functions and P functions and D functions, and then you put them in the solid, you know a whole lot about the symmetries. And so you can classify them into PD sigma, pointing toward each other, and PD pi, where the orbitals are pointing not along the line between the atoms. Things like that. So So then there's three centers. It's when you have two-way functions and a potential. And I just didn't show that for ease. But it's really useful then to use these kind of ideas, and then you can make the Slater-Coster tight binding kind of picture where there are parameters, and the two-site approximations are really nice in many ways. Like the overlap is a two-way function problem. The kinetic energy is a two-way function problem, and the potential then it's harder, but it doesn't necessarily have to be cast as three functions. It can be a potential expressed one way and then two wave functions. So you get a long way with this kind of approach. And here's an example of the comparison of a good calculation of local orbitals in siesta and this linear APW method that's presumed the best for this problem, or barium atoms and barium titanate. Where these are the ferroelectric minima. And those curves are for two different directions, and this would be the stable point. So anyway, that's the message. You can get the same results if you really work hard. And the tight binding, you probably know, is really nice for getting things. And I just like to skip through here. I put this up because I like it. But like the graphene problem is this pretty one where this is 2 carbon atoms per cell, but I've colored them differently because they're inequivalent. And it could also be boron nitride. And the wonderful thing is that the Hamiltonian involves only one number. It's just the connection, hopping between one site and the next. So going back, so there's one pi state sticking out of the plane, but in that sense, it's spherically symmetric around each of these points. So it has the same symmetry as an S function. So there's only one number that characterizes the hopping from a dark site to a open site. So one number in the entire problem, and that gives you the nice feature that you just know that we have these Fermi, at the Fermi energy, there are these Dirac points that have this linear dispersion. So it just pops out of that simple calculation. This was Fermi energy in some case that I've now forgotten, but it was, it's when you've doped it away from the exact point. The Fermi energy would be exactly at that point if it was the pure system. Okay, I had this for a different talk, for how you make nanotubes, rather than how you characterize nanotubes. But we don't have time to go through that, so I'm going to skip it. However, I wanted to make this point. You do these local orbitals, and you miss something. You just miss them. For example, there's a beautiful excited state that's enclosed in the tube. It's just like a particle in the box problem, and it's just, you miss it if you stick with local orbitals. If you do plane waves, of course you get it with thousands and thousands of plane waves. So it's a very nice example of being careful. So then the summary basically is that they're very useful, and Gaussians are useful, and these numerical orbitals are useful, and then there's some other forms that are useful too. And I might point out that the MD code, whose name I've forgotten, by Jörg Hütter, is a very efficient one that uses Gaussians instead of plane waves. And Siesta is fixed so that you can do quite accurate calculations. And then that's easier than plane waves for some big systems. Okay, what do you think this is going to say? They're general, and they don't care what kind of atoms are there. And the bad thing, of course, is they don't care what kind of atoms are there. And it requires a lot of plane waves to bring in that behavior. But the efficiency of these codes has just gotten so good that they just kill you. And you can just do them. And other codes take their properties and then become even more efficient. So I want to come up, I think it's the next slide, to say something about the connections between these methods. Okay, this is it. I say that every plane wave method that you see can be thought about in this way. This is the scattering of a plane wave from an atom that has a spherical or almost spherical potential. And this is something that's in scattering theory in textbooks. Incoming plane wave scatters, but it has the same, that's supposed to be a square. Say it's the same kinetic energy because it's an elastic problem, like scattering off a core state. And the only thing that can happen to this plane wave after it's gotten out of this scattering area is it has a phase shift. It's kind of a shifted phase compared to what it would have been if it didn't, if it wasn't scattered. And this is the message, that all these problems will be basically dependent on what happens inside this atomic region in detail, but the final effect is what happens when you go in and what happens when you go out. What happens in the middle is not needed in detail if you only know this point. So let's keep going and say, now I've already said this, the problem with plane waves is that you've got the atoms there. And it takes a lot of Fourier components, so we look for something different. We look for a way to handle all those high Fourier components. And there's several ways of doing it. I'm just saying this again, that we really want to determine the properties in a way that's not just expanding in plane waves. Okay, and here are the three ways. So you could replace the cores with a pseudo potential, so now it's a weak potential, and you just do plane waves. But you replace the atom with a pseudo atom. The ultrasoft and the PAW then add something in this region. It's not just a potential, but you have a thing that acts like a potential, but then you add something more. The PAW is now very popular because what it adds is essentially the core orbitals. So now you've got all the orbitals there. The augmented method, on the other hand, or I should say the original augmented method, the augmented plane waves, literally stops the plane wave at the boundary and continues it inside as a spherical wave. So I actually meant to put this later, but I forgot to change it. So I just wanted to put in a few words about these efficient methods for using plane waves. And everywhere else I just talk about, almost everywhere else, just diagonalizing the matrix, because you get the basic ideas. But to do it efficiently, it's this gorgeous idea of using Fourier transforms. So and that's just, oh man, I made several mistakes on this slide. But anyway, the key thing about a huge difference with the APW method is that the wave functions inside the sphere are not plane waves, and the Fourier transform tricks just don't work. If you have a smooth function that goes everywhere, including inside the spheres, then you can Fourier transform that, and you get, it's really the idea. And then you add the sharp functions later. in the ultrasoft and the PAW. But that's the big difference between computation is the big difference between these methods and the Slater APW method. So now I'd like to leave this with just very general comments that there are many iterative methods, and what I'd like to say is that they mainly go to Jacobi in 1848. That the idea is you apply an operator to a function and you get a residue. And in this case, if it was the exact function, the Hamiltonian minus the eigenvalue times the function would be 0. But if it's not 0, then you make one of many possible iterative methods to improve the wave function until you get 0. Okay? And simplest is Newton-Raphson or steepest descent. The much more efficient is conjugate gradient, and then this really long series of methods where this discrete inversion and something subspace and the Davidson algorithms, they're really very efficient. Yes?
Which book are you?
Oh, mine. Sorry. Excuse me. Somewhere back in there, I may have forgotten it, but it was just as I have some things that refer to the book, and I keep them in because I just wanted to point out where they are. So pardon me for being kind of inconsistent in this. So this is a place where I just said, oh, I can't possibly describe these. Okay, but I love that idea of the Fourier transform for this problem. And so we have a kinetic energy piece that's diagonal in Fourier space. We have a potential that's diagonal in real space, which means you just multiply a potential times a function at one point, and then sum over points. And the fast Fourier transform allows you to start with the potential in one space, operate on it by the two functions, and bring them back together. And and you never have a matrix the whole time. In each space, you are just multiplying the coefficient by a number. So if you've got 10,000 by 10,000 matrices, that's a lot more efficient to do it this way. Anyway, that's one of the things that Carr and Parinello did that really made the field different. And I wanted to make the point that grids appeared here just quite immediately. That once you Fourier transform, then you do part of the problem on a grid. So now we have a way of looking at grid methods that's like inverse to what I would have said many years ago. That if you look at a pure grid method, you can get the kinetic energy by a finite difference formula. And you always stick with a grid. Never go to Fourier space to calculate the kinetic energy. So with the grid, it's great for localized systems because you don't have to have points out in the vacuum. Whereas for plane waves, you have to have a lot of plane waves just to get 0 in the vacuum. So anyway, if we think about this, now we see the connections between the methods. Think about it from the grid point of view, we're just stay on the grid and we calculate the kinetic energy by finite difference. And the potential energy is simple. You can think of it as that, or the alternative would be to go to Fourier space and calculate the kinetic energy that way. So it's a comparison whether you want to calculate the kinetic energy by a finite difference or by a Fourier transform. And that's the difference in the methods in that overall sense. So if you do it by plane waves and you do it right, you have a variational theorem. If you do it by finite difference, then you're not guaranteed whether you're above or below the correct answer. Okay, moving on. Back to superpotentials. So now how do we use that idea of phase shifts? Pseudopotentials, you do something in the atom and you use it in a solid. And the something is designed to be as clever as possible so that it'll carry over to the solid as well as possible. And here let's see if I did on the next slide. Yeah, here. Let me just skip that previous one because I made a change and put it here. So the norm-conserving pseudopotentials have this beautiful property. So you calculate them in the atom, and basically here's the potential, and here's the pseudo wave function that's equal to the real wave function up to some point, and then inside it's just made smooth in an arbitrary way that's convenient for some problem. But the important part is it's the same outside, which is where the bonding occurs. And this is exactly the same idea as getting the phase shifts right. You say, I don't care what's going on in this region, except for some rules and things. All I care about is the function out here. And you can work that out strictly in terms of scattering off this atomic region, and all you care about is what happens outside. And the norm-conserving idea is just completely impressive, I think. How many of you have looked at why norm-conserving is important? What that word even means? Who knows what norm-conserving means? 1, 2, 3. Do many more of you have you been through what norm-conserving would mean? Right. That's what I expect. So why in the world it seemed like everybody would conserve norm, right? Which means normalized. But that's not the way old pseudopotentials were. The idea of the first pseudopotentials was that you just get a function that obeys these logarithmic derivatives, and depending on what you put inside, it didn't have to, the whole function did not have to be normalized. It just depends on what you put, what the function looks like inside. But if you require that the integral of the number of electrons in this region, I should say the wave function squared, is equal to the integral of the wave function squared for the all-electron problem, then you get an extra property. Number one, it's easier because this function is identical outside. It's not multiplied by some factor. And number two, there's this beautiful theorem that, result that comes out that's really nice, is that if you construct it in this way, you find some function that goes inside and it satisfies this condition of the norm that I mentioned. And here's just the first step of you find a function and then you find a potential that gives you that function. Okay, so you just invert the problem and you get the potential that will give you that function. And you've done this at one energy, right? Like it's the bound state of the atom. And so with that one energy, you know for sure that the function is absolutely the same out here. Yeah, that's just easy. But that's not the energy you want in the solid. The energy is not the same. And what this norm, let's see, where is it? Sorry. Elegant proof, right here. That if it's norm conserving, then this matching condition at the boundary, which means that's the reason that these functions would be equal, is valid not only at this one energy, but to linear order in energies nearby. So in one step, you've done something and made the problem easier and better. And all of it was happening back in the atom, where it's pretty easy to do the calculations, and then you use it later in the solid. So even though the energies in the solid are not the same as in the atom, it's a linear order, they're still correct. So we get at this. That's the transferability idea, that they're as correct as you can make them, as in transferring from the atom to the solid. Okay, so here's a couple of functions that's gotten off of this website, and I really like this. These are on the right-hand side of the pseudo-functions and the left side are the all-electron functions for S, P, and D of iron. And if you compare them, you see that they're just what you want, almost, for the region outside this core area. It's hard to tell the difference between the two functions. Inside, of course, they're different, and the fact that this d-state is different to that extent affects the things like the magnetic moments and things. So that difference was one of these limiting factors, and that can be improved by these ultra-soft and other methods. And you just can't do much better, because you have to sit outside the maximum, and then you're just trying to make something that attempts to get the maximum right. Okay, this is just the whole picture of all these potentials will give the same results. It's really nice. And sorry, I use this in class. I referred to textbook. Okay. So I just want to go quickly then the next step. If we have this behavior inside this sphere, then one way to improve that greatly is just a different method that makes a smooth potential inside the atom that goes all the way through the atom, then plus some other function. And in the ultrasoft potentials, you just add some function there that will represent, for example, that D function and the iron. For the PAW, you still have this smooth function, but then you add something that corrects and gives the atomic function. And so you've broken it up into two things that add together. And you work only on the smooth part in the calculation, and then you should add the other part.
So I missed something on the pseudo-potentials you had for iron hub. I mean, were they different potentials with different angular momentum, SP and D, or?
Yes, I apologize for skipping that point. So this is the pseudo-functions, and since you construct them for each orbital angular momentum, they give different potentials.
Right.
So I've just...
So it's a bit more complicated than a simple pseudo-potential.
Forgot to say that. Mm-hmm. So you just have to live with that. That you just have to decompose things in an angular momenta, and then it's kind of a non-local potential. Thank you. And sorry, there. And here was, I've already forgotten what this was, excuse me. That's different potentials for one angular momentum, and all those potentials will give the same result. And that one, I think, is carbon, and I forget sorry, I was just trying to make a general point, but you get the same eigenvalues and tails of the wave function for all those different shapes of the potential.
And are they all norm-conserving as well?
I think they're all norm-conserving, yes. And now I remember the point. That's angular momentum 0, and that's angular momentum 1. I think I said that right. Excuse me if I didn't. So PAW just does the same thing. It just adds those atomic-like wave functions, and I don't want to go through the equations. They just get harder, but you get a lot more out of them. Okay, same slide. You should agree. And the place where you don't quite agree is the is one I mentioned before, like the calcium fluoride, and to some extent the iron. And now we can start looking a little bit more closely. When you add those atomic functions in, then it's starting to look a whole lot more like the results if you do these high-quality APW calculations. And compared, sorry, oh yes, and here's the moment in iron, and for some reason I didn't do that, sorry, just forgot, or rather it wasn't in the table. So this is one of those places where when you look in more detail, the norm conserving potentials are having a problem, you know, in detail. When you add in the atomic-like functions, and it's PAW, it's gotten a lot better. And also the ultrasoft superpotentials. Okay. Man, I'm not getting any questions out of you, so I ought to go slower, I guess. Yeah. Oh, I got one. Good.
You said that the PAW can be better, but it's more difficult. In what kind of systems is it better to use that?
Well, I guess it's not worse in any way because you just add this feature that's more realistic. But it's in the transition metals, and that is most important. And for calculational purposes, this ultrasoft pseudopotential is really useful in atoms like oxygen. That's where you didn't really need to get the core functions, but you get the shape of the S and P orbitals much better. So it's really useful. I was reminded earlier about, I asked you a question, so I want you to be thinking about it. What about the Mermin functional? Why is it harder to get all the thermodynamic variables than the ground state? Why is it harder to get the temperature dependence and the free energy than just the ground state energy out of a density functional calculation? Yes?
Because you variational principle improves that if you minimize the density, you'll get the absolute ground state, but there's no similar thing for the first excited stage.
Okay, I think but it's a two-step argument. There is a variational principle for the free energy. Yeah. Let's see. But in terms of the ground state problem, that involved excited states, right? Well, right, you can minimize the free energy. So there would exist in principle a way to do it. But I think you're onto the right point. It's a lot harder to get the things that have to do with the temperature-dependent excitations than it is to get the ground state. Like, for example, the specific heat of a metal depends on the effective mass, you know, at the Fermi energy. Be the slope of the bands at the Fermi energy. Or I was reminded of a magnet that has spin waves. And it's just a lot harder to find some functional that would give you that, whereas the ground state functional, at least it's just an average over everything that's happening to all the electrons. And so it seems like it's not as hard to get that. So that's why I claim that there's hardly anyone that uses the real Mermin formulation. Not anybody I know. Okay, so let's get back to this. Yo, please.
Is it that it's just very hard to get that specific amount of detail?
Just hard.
But it's possible?
That's one of those existence theorem things. I think we're not even close to getting something that would be That's something that would work for some systems. And then, you know, that kind of defeat the purpose. Yeah. Yes.
Is the magnetization, how's that gotten?
How's it? Oh, this is just spin density functional theory. So, so when one has a spin exchange correlation as a function of the up and down spins, and so for iron, it turns out as a qualification that you get the lower energy state is to have it polarized, more ups and downs, and then just the calculation grinds forward just like an ordinary calculation. And the only thing that went in was how did the exchange correlation energy depend upon the number of up and down spins.
You also...
Yes?
And you also said something about the core section of the wave function, like, within the core, wave functions don't match or electron. And you said something about, because of this, the magnetic moments are wrong?
Good.
Is that related? Or?
I probably said it in a way that's maybe hard to reconcile, but like if you get the average number of electrons in the core region right, then you got the moment right, because that's just the interval. I mean, if you have the average number of up minus down correct, then you get that number correct. But then you start asking, how good was the exchange correlation part as a function of the density that you have in your calculation? And there's some cases that you can start imagining some cases where it goes pretty badly. One of them is when all the spins are pointed one way and there's none pointed the other, and then you have to go through the consequences of that. Okay, so there's several things, but I see you're frowning, and I don't have a good answer. Yes.
You mentioned that the field potential is constructed for each angular momentum.
Yes.
Yeah. Does this mean in DFT code the Cohen-Shum equation is solved also for each angular momentum?
Yes. Right.
The plane wave is actually a project on each plane wave, I understand.
Exactly. You have to project a plane wave onto the SPD functions and then treat them separately. Yeah. The computer program gets about twice as long. It's a pain. But once you got it in the computer program, it runs.
Does this mean actually in DFT code, we first get the project density of space, and then we sum them up, get the total density of space, or we get the total density of space first, and then project into the angular momentum? Which way does DFT code?
Normally you do the first way. You just get the effect on each plane wave, right, and just then add them up later. There are clever ways to work backward. Add them up first and then have the projector to operate on them. But I think that's way harder to do that. That's what I think.
What's the major difference between ultra-soft pseudo potential and the PAW?
It's which function you put in this region. So the PAW is you carry around more stuff. It's a little harder, but what you carry along is something that's close to the real wave functions. And whereas in this form you're still making something fictitious on the inside that is just try to make it more accurate and less computation. So this function can be smoother than the full function. So you just have to do less plane waves. So it's a little bit more than just the computational help. but that's the main thing. Okay, so APW. And so my phrase I like is it's the best of both worlds and it's the worst too. Because the best is you really treat them like it should be. And between the atoms, the wave functions are smooth and plane waves, and inside they're spherical and angular momentum. And the bad thing is programming that and finally using it well. And what it actually is, it's kind of interesting how it was actually done first. What it is a matching problem. I think I have that on the next slide. You get nonlinear equations out of this. Oh yeah, sorry, this is my good and bad. So I've already said it, it's really the functions that you like, but it's hard to use. And the thing that Ola Anderson did in 1975 was to show how to linearize those equations. So let me show you why it's nonlinear. By the way, the reason I put in so many slides was that the idea that could be available and not just blow them by you quickly, so that these can be made available. Okay. So, sorry, it's got to go a couple of steps. So the first is this muffin tin idea. And the first step is it's just a division of space, no approximation. The second step was the original APW, where you just make the potential exactly spherical in this region and exactly flat in between. And that's called the muffin tin approximation, or muffin tin potential. And the new programs don't do that. They let everything be varying, but it's much easier to explain in this form. And it's fairly hard to do those next steps. And in this form, we can see exactly what's going on. Each function is a plane wave outside, and inside it's the matching of a plane wave to spherical waves. So you know how to do this. At Illinois, in our freshman physics class, we got people to do this. It's doing quantum mechanics and a particle in a box. So I can reach up here. So you have a particle in a box. How many of you have done this? It's a finite height, so you do a curve that's a cosine, but it doesn't go to zero. What do you do next? I'll say this is zero for the wave function. What does the function look out here? Right. So here it's an exponential, and here it's a cosine. And not the same. Okay, fine. And what do you do? How do you get the solution? Boundary?
Boundary conditions at the side, but match.
You got to match here, right? So you have to match value and slope. And how do you do that? At least for our students, we said, change the energy. If you change the energy, you know how this function changes, you know how that function changes, and you just go until they match, and then that's the eigenvalue. That's the eigenstate and the eigenvalue. So you change the energy until you get a matching. Okay? Non-linear problem. You just do it, and that's exactly what is done in the original APWs. You don't know what the energy is. You've matched the plane wave to spherical waves, and you know that the solution is a linear combination of those plane waves and spherical waves, and you have to choose your energy until the entire solution matches on the boundary, or at least it goes to zero to the as much as you can make it for a finite basis. And so a clever way to do this is to have a band structure. This would be K. And so one way to do it is to find out the K that corresponds to that energy. So we always do it the other way around in other methods. Choose the K and find the energy. In this case, if you choose the energy and then you adjust the K, which means you're adjusting which plane wave you're dealing with, you can find the value. So it's actually, these methods are cute. But it's a hard problem, and it's just painful. And so this is where, sorry. Ah, that was the point, excuse me. That was to fix E. Okay, so I've already said it. So you have to scan in order to do this calculation, and you have to do that for each band. Like we have a bunch of D bands and S bands, and you have to do it for each one. And then you have some proofs that they're orthogonal, but of course they won't be quite orthogonal. So there's all kinds of stuff like that. So I'm not going to say, here's a couple of results. This is one of these early calculations. It was really done earlier, but this is the computer, where it was done well with computers. And then later, the experiments came along. So this is, Mr. Burdick was really quite clever in choosing the potential that went in there before density functionals. And you get all these pretty results with transition metals, so you just characterize these D bands, how the Fermi energy crosses the D bands for all these systems. So, it's really nice kind of results that have been done. And horribly complicated things, but because you can do it, and do it accurately, and you can deal with those sharp variations in the copper states and the oxygen and the lanthanum and ytterbium, if you want to put it in, because you can just do all those things, and no pseudopotentials, anything. So as long as you've got a problem like this is the way to go. If you want to do molecular dynamics, on the other hand, getting the forces out of this method is something else. So different problems, different techniques. Okay, so I'm going to get to linearization in a minute, or at least something. So anyway, I'd like to be really clear that I think I also did make one more difference, that the LAPW is, APW is the most general form, and I've given you a little bit more information. In order to actually get an accurate solution of matching on the boundary, you need to use high L components. You may think, oh, it's iron, it's SPV. But to actually match, you need to put GFGH to actually get the solution. It's counterintuitive, but that's what you actually have to do to get a good solution. And then you have to go to higher numbers of plane waves to just the whole bit is, it's not as easy as you might think. On the other hand, what it does is it calculates the stuff inside that sphere, and it doesn't assume that it's like an atom. To the extent to which it's not an atom, that method is done better. And that's good for transition metals in particular. These other methods, like the pseudopotential and most implementations of PAW, have done something from an atom and assume it transfers over to the solid. So check whatever method you're using that there's more assumptions in these methods than in the original APW. Yes?
Plus, the APW isn't going to deal with kind of technical things that aren't atomically based, right? So, give an example of the graphene cheap, nano cheap
Yes?
You said there was some kind of state in the middle. You're still not going to see this to the LPW graph.
Oh, yes, you will. Depends on, we have to be sure that our plane waves extend everywhere, but there's actually even a big, widely used years ago, method for molecules that was APW, and that was gotten by drawing a big sphere outside and saying little spheres around each atom and a big sphere around the whole thing, and making a method that would work. So if you allow the plane waves to extend out everywhere, then they'll find those states that abound in the middle of that nanotube.
But that's still expensive because you've got plane waves in it. And
Yeah. You got it. There you go. But it gives you something that you didn't get the other methods, and that's the shape and details of those functions inside the sphere. And that's why this method is in general better for the transition metals, where the D states, so it's mainly inside the sphere, but also stick out. And so they're just better in some cases. How do I change this? Let's see. Try. This was supposed to be first. There's another set of methods that's really pretty, and it's the methods that match to spherical waves outside. And that's just as good, except that you're getting this interstitial region with spherical waves. And the original ones was a KKR, Kringle Cone Rostocker, from the 40s and 50s, that did this by multiple scattering technique. You have say an electron that starts at this atom and it propagates to the next and it scatters and scatters, and you can make the solution of the problem by essentially a multiple scattering solution. And for the electron to propagate to the next atom, if you assume the potential is flat in between, you get this wonderful simple result. This is the Green's function for the electron propagating in a flat potential. It's a cosine. So you start at one point and you get the function at any other point just simply as a cosine. That's really nice. So Green's function methods can be really simple. And so once you got that, you can really solve the problem in a very, very clever way. Need fewer functions, etc. And here's a quote I really like. This is from Simon. It's basically this is the most elegant method there is for solving band structure problems. And it is. It's just really pretty. And the only problem is it's really hard to get away from that flat potential, because then the Green's function gets real complicated. So it only recently has come around that people have made general purpose, general potential KKR methods. But this is the original method that was used for basically the first density functional calculations. I don't want to go through this in detail, but this was a calculation to the I thought they were earlier than that. Anyway, some of the early calculations, I think these were the first that really showed that the density functional gave you amazingly good answers for the lattice constant, the bulk modulus, and the binding energy for transition metals. So this was one of the works that really started the field. And they use a KKR method. LMTO has, you should just check some of the pretty things that it does. You go read Ole Anderson's papers and you'll have a hard time getting it. But it's really pretty. He said, well, if the functions don't have far to go to get from this atom to that atom, then I can approximate for k equals 0, in which case it turns into the Coulomb problem. Del squared of this function is equal to 0. And he made analogies that was just like charges. You could find screening, you could find all kinds of things that just come out.